So today, like I said yesterday, today's a pen and paper day, and all I really mean by that is, you know, we're not going to be using a text editor really. I have an IPython terminal open here. That's just to do calculations as they come up, and otherwise, I'm mostly going to be writing in this Paint program, and um, I'm going to try to explain some reasons for that. There are ways that we could look at some of the conditional probability materials through the lens of things that we code, but I think it actually gets a little cumbersome, and there's a future version of this where we create a simple sampling model, for example, that uses some kind of conditional probability to update the form of sampling, a process that you can refer to as dependent sampling, something like that. I think I made an allusion to a form of dependent sampling a few days ago. And when we talk about technical interview stuff, I might invent a sort of mock technical interview that includes some dependent sampling, just because it's cool to see that kind of thing sometimes. But for today, we're going to kind of take a high-level view at first on this idea of frequentist thought and what some people would think of as an alternative to frequentist thought, which is Bayesian thought. At the end of the day, it's all under the umbrella of statistics and probability. And so, personally, I don't make too much of a differentiation there. Some people make a very strong differentiation, and you could argue that there are, in the data science space, there are a lot of models that use Bayesian approaches. In some sense, a lot more models that we see, on the regular that use Bayesian approaches than frequentist approaches. But we qualify things through a frequentist approach in a lot of cases. So, I'll speak to that a little bit. We won't go too deep into it, but it'll be some food for thought. And then we're going to get into how to think about conditional probability. How we've described it up until now, and then how we're going to formally define it through Komogorov's definition. And then we're going to build on that into the law of total probability, and we're going to look at Bayes' theorem problems following that. Turns out that most Bayes' theorem problems, like textbook Bayes' theorem problems, are going to almost be just law of total probability problems. Like the crux of the problem is usually the calculation of a total probability. A marginal likelihood is another way that we call that. And then we're just going to run through a bunch of problems. So that's what's on the agenda, and let's just get into it. So Bayesian versus frequentist thought. I want to be, just clear in saying this. I'm not going to speak too deeply on this. I'm going to give sort of a passing impression. So when we're doing frequentist things, a lot of the time we're assuming that if only we knew the entire population, that there is some population of material out there to know, right? Like the height of every tree in a forest, something like that. If only we knew that, then we could calculate the mean, we could calculate the variance or standard deviation, and we could, very sort of accurately describe the parameters of this population. Unfortunately, we are limited in our ability to sample, right? And so what we do is we create a representative sample. And from that representative sample, well, we get x bar and we get s squared for the variance. And our goal, a goal that we have, is to have our x bar look as much like mu as possible. And, that follows to reason that hopefully our variance is inclusive of the population variance, right? So that's a way of thinking about frequentist thought. And there are kind of incredible things that come out of this. Things like, there's a frequentist approach to hypothesis testing, right? Where you're considering whether or not the results of some experiment, depending on how you structured the experiment, is how can we gain confidence? How can we express our confidence in the results of that experiment? Well, we do that in a frequentist way through various tests that we have via the normal distribution or t-distribution, chi-square tests, things like that. So underlying frequentist approaches, we have probability theory and an idea of some theoretical distribution that's out there that we can approximate through sampling. And obviously, the bigger the sample, the better statistics that we can build. And the more times we can run an experiment, potentially the more confidence we have in the outcome, right? So a frequentist approach, in its foundation, we are trying to figure out if the population that we're sampling is at times different from a value that we are hypothesizing, right? And when we say hypothesis testing, that does start out with a hypothesis, right? And we are, disproving that hypothesis or sort of letting the hypothesis pass. We have a couple choices there. There's multiple hypothesis tests, different ways of approaching that, but at the end of the day, we're assuming that there is some set of parameters that are discoverable if only we can access all the information available. And I think that is a very frequentist way of thinking. So a Bayesian approach is a little bit different than that. In Bayesian thought, we don't have necessarily an idea that there is this static population, right? Instead, we are we're going to think maybe in terms of observations. So we might take a guess, and then we observe, and we update the guess, right? And then we observe. And we do this sort of forever, and we settle into some kind of confidence. We sort of, as we go, we settle on something like a parameter, right? Something like a parameter. So you can imagine if we were to look at one person in the population, right? And they're 6 feet tall. We might make the guess that the average human height is, I'll just call it x bar. We might make the guess that the average human height is 6 feet. Well, let's look again. Oh, well, this person's like 5'4", right? So at this point, we might update our x bar, right? So, can I convert this to inches really, really fast? The average of that would be, oh gosh, would that just be 5'8"? I think it would. Well, let me be wrong about this. I don't really think in terms of inches. So like 5'8", and then we might observe again, based on our prior belief. We might update this belief with the next observation. And we can go on and on and on like that forever, right? And we have this cyclical process. And eventually, what we're probably going to see is that we settle on some value. And we've gained confidence in that value through the iterations of this process. Okay? And the way that philosophically you might think about Bayesian thought is that we are updating a belief, right? And I think there's a power in this, right? Because let's say you're observing behavior of cell phone users, right, in a population, and maybe you're thinking in terms of minutes used. You know, if you have minutes used as a value that you are collecting, it might be better, instead of looking at the minutes used for all time of your population,
The audio's not working either.
Sorry, one sec. Is there an audio issue? Okay, I'm just going to go forward. And if you can Slack, if you're having an audio issue, try slacking Clark. He might be able to troubleshoot really quick, because I think he's on the call as well. Okay, so let's think about this in terms of, say, minutes used. You could look at your whole history of minutes used, starting in, well, I don't know, let's say 2004 through the present. And you could say, well, there's some average number of minutes used, right? There's some average number of minutes used that is the sum of all minutes used, divided by the number of users. And that's going to give you some value. And you could say, well, I think that's the average number of minutes used. But, if you're in 2021 right now, you may not think in minutes used anymore, right? That's something that even as a value, we don't think about minutes used in general, not most of us. And that's because the technology has changed, and it doesn't mean that minutes used isn't a valuable piece of data to collect for a company. But, we might want to instead constrain this to a window of time. And as we progress forward in time, we shift that window of observation. And ultimately, we have something that is more accurate to the time. We continually update our belief. And then we can ask questions related to that as well. We can use as a foundational principle a belief that we have, as opposed to something that is drawn from a static population. And so the kind of inference that we perform here is not really from a static model. It's from updating information based on observations. And when you get down to it, there are a ton of, I could even just show you a paper on a model that I'm pretty into. So this isn't going to be entirely clear, but this is an algorithm that is based on a Bayesian approach, where we have a conditional probability that we update based on new observations within a data set. And we can kind of see right here that there's something given something else. This is a Gibbs sampling. If you're familiar with Gibbs sampling, which you don't need to be at this stage, this is a Gibbs sampling approach to update beliefs that we have about a set of data. And this is fundamentally Bayesian. And in fact, this whole model, which is called LDA, is Bayesian. And we don't even talk about it in terms of it being Bayesian because the approach of Bayesian thought is everywhere in machine learning. So I'm going to leave it at that in terms of the kind of philosophical side of this, because we're going to get into building a foundation, a mathematic foundation for conditional probability. And we're going to ultimately end up applying this to Bayes' theorem, or applying Bayes' theorem to some simple problems. So let's think about this idea, conditional probability. And let's think about how to express this symbolically. So simply, a conditional probability is the probability of one event occurring, given that another, some other event has occurred or will occur. So if we think about this, simply mathematically, this is we could say it like this: the probability of A given B, and that's how we read that. Given, right? The probability of A given B. And we might assign to this some event. So what is the probability of, say, drawing an ace of spades given that you drew a queen? So this is a question we can actually answer. We can go through this and answer this. We can reason this out, in fact. I'm not going to do that here because we're going to do a bunch of different problems, and some of these problems we'll take a little bit of a slower ramp than this. But this is the kind of question that you can ask, and you can put it in the real world. You can remove a queen from a deck of cards, and then you can ask the probability of drawing an ace of spades. So offhand, what do you think that is, actually? If I'm just saying that, what do you think that probability is? And you can express it as a fraction. Yeah. So intuitively, this idea is not hard, and we can think about it kind of in terms of a timeline, even, which is kind of nice. So this won't work in every case in terms of the ideation of it, but you drew a queen, right? You drew a queen at this point on the timeline, and at this point, you're drawing another card, and you're asking, well, what's the probability of an ace of spades here? Some prior event has occurred. Some previous event has occurred, and because of that, we have altered this. If we were just asking the probability of drawing an ace of spades, that would be 1 out of 52. But we have modified the space from which we're drawing. We've built a new universe, and that universe does not contain one of the queens, and it actually doesn't matter which one, right? The way that we frame this. We could turn this around and ask the probability of drawing a queen, given that you've drawn an ace of spades, and that's going to be just a little bit different and not hard to figure out if you just think about it for a second. So we're going to be working with this idea, the probability of A given B. And we're going to start this by, going back to our friendly neighborhood Venn diagrams. And so let's say we've got A, and we've got B. And I'm just going to put some values in here. The area of this part of A, let's say, is 1. And this is an oversimplification, but we're going to go with it. The area of this part of B is 3, and the shared area is 2. And, if we want to consider the area of our sample space, which we'll just call S, let's call that 4. Now, we don't really need that 4, but we're going to keep it. So we're thinking about this in terms of initially the probability of A given B. And I'll just set this up here. And if we're thinking about this in a very simple way, we can say, well, the probability of A given B is going to be, let's think about B as being the universe that we're constructing somehow. And, well, what is the universe of B? We can think about maybe that in terms of area or items that are in B. And then A given B sort of is naturally the intersection of A and B. So we can think about the probability of the intersection of A and B, and we can put that over the probability of B. So, just looking at this plot up here, the intersection of A with B, well, we have an area that we've described there as being 2. And I'm just talking about this in terms of area. I think for me, it's helpful to think about probabilities as probability areas, depending on the problem. So that looks like 2 to me. And then if we're constructing B, that looks like 2 plus 3. And at the end of this looks like 2 over 5, right? And so in this visual representation, we can think of the probability of A given B as being 2 out of 5. So something that comes up out of this, the emergent property that we're looking at is what we refer to as Komogorov's definition of conditional probability, which is simply this probability of A given B being the probability of the intersection of A with B over the probability of B. So that's kind of our starting point. So let's put this in terms of a problem. And I'll just snag this problem and bring it up here. That might be a little bit small, but I'll read through it and help us try to get an understanding of what's going on here. So, oh, there we go. Okay. Didn't know why that wasn't erasing. So a survey was given to a number of students regarding their pets. 40% of respondents reported owning a dog. So, okay, this is 40% of all respondents, and we can start thinking, we can start writing information down. So the probability of dog, and I'm just going to say, I'll just do it like this. The probability of dog is 0.4, right? 45% of respondents reported owning a cat. So the probability of cat is 0.45. And 25% of students responded to owning both. Okay, so that would be the probability of dog intersect cat, which would be 0.25. So if we're thinking about this Komogorov's definition, we can answer a question such as, what is the probability of a student owning a dog if we know they own a cat? We can answer that fairly easily. We've got, well, let me just write down this definition again. Probability of A given B equals the intersection of probability of A with B over the probability of B. And here we're asking, what is the probability of a student owning a dog if we know they own a cat? So I like to write, there are different ways that people will write this down. They might say, let A represent dog and let B represent cat. I personally don't like doing that. I have a hard time reading it. And what I do instead is I say the probability of, owning a dog if we know they own a cat. This is just dog given cat, right? The probability of dog given cat. And then we can follow this template. We can say, well, that's the intersection of the probability of the intersection of dog with cat over the probability of cat, right? So we're going to think about this universe of cats, and there's going to be a subset in the universe of cats, right? If we go back to our, we say that, if we think about this again as, this cardinality of A over cardinality of S, if we step back, we are thinking only in terms of the universe of cats. And that universe of cats is actually 0.45 of everything, right? So we can think about this as normalizing and bringing into the bounds of 0 and 1, right? Bringing into bounds this intersection up here. Because if we're thinking about, the probability of owning a dog given that we know they own the cat, we have limited the space, right? We've got this whole space of animals, and we're like, well, we're only really considering the area of cats, right? And then there's going to be a certain amount of people in this area of cats that own dogs, and that's what we're looking for. We're not looking for people who own dogs, who own cats, on its own. Notice that this is a much smaller area in relation to the whole. We are only relating this back to the universe of cats. We are throwing away the rest of it, and we only, we're getting the probability of this in regards to this, right? So this would be our S, this would be our A, and we can think about it that way. So, if we just fill these numbers in, that's going to work for us here. So, what is the probability of dog and cat, the intersection of dog and cat? That's 0.25. What is the probability of cat? That's, probability of cat is 0.45. And if we plug that in to, I'll just grab my terminal. What was that? It was 0.25 divided by 0.45. Looks like that is a probability of 0.55 when we break it down that way. So, I'm getting 0.25 because that's the probability of owning both a dog and a cat. Okay, but notice in this, if we kind of add these up, right? Probability of owning a dog is 0.4. Probability of owning a cat is 0.45. We've got 5% in there. We've got 5% of these people who don't own either, right? And so the intersection of dog and cat has meaning just based on that. And so when we're looking at this, this is the subset this we can think of as strictly a subset of people who own cats. And so if we ask the question, well, given that we know someone owns a cat, what's the probability that they own a dog? Well, we're going to take this this intersection and normalize it, or standardize it to back into the range, because currently it's out of scale. Currently it's much too small. We're going to scale it back up to be between 0 and 1 by dividing by 0.45, which is the universe of our cats. So that's kind of a simple example of conditional probability through Komogorov's definition. And Komogorov's definition is going to come back in Bayes, and we're going to see that actually Bayes is a rethinking of Komogorov's definition, as it turns out. And I think that's kind of an interesting thing. So if we start to rewrite Komogorov's definition, which I'm going to do right now, the probability of A given B is equal to, right, that intersection of A with B over the probability of B. Oh, you know what? Let me answer this other question that's in here. Can I clarify why it is the intersection and not the union in this example? Let me try to. So if we go back to this diagram, right? We've got this diagram. If we're thinking about the event B having occurred, there are things that are in A that are not in B. And we don't really need to consider those things. If we're asking the question, what is the probability that something in A occurs given that something in B occurs? Well, that's this, right? This is the area of consideration, the initial area of consideration. And we're like, oh, well, that's the only place where something in A occurs that could have something to do with something in B occurring, right? And so we have to consider that. And because this is given B, right? This is given B, then we reduce our sample space. We reduce our sample space and constrain it to just the events that can occur in B. And so that's where we get this the intersection of A and B over the probability of B. So that's hopefully that makes that a little more clear. So we can rearrange this formula a little bit, and there are some cool things that we can observe here, right? So if I just multiply both sides by the probability of B, so let's do that. So multiply this side by the probability of B, multiply this side by the probability of B. Do that. And we can see here that the probability of A given B multiplied by the probability of B is equal to the intersection of A with B. So this is pretty powerful notion, and there's something that we can get out of this that is a qualification of the idea of dependence. So there's dependence if this is true. And here's maybe the a kind of wild thing. We can think about this also in terms of independence. Okay? So the way that we might do that, if there's independence, then the probability of A given B will equal, right? And I'll write this down. The probability of A, let me just be clear. So in terms of independence, if we're trying to talk about the probability of A given B, if A and B are independent events from each other, then this is just going to be the same thing as the probability of A. And we can take this a step further and say, well, if the intersection of A with B is equal to the probability of A times the probability of B, then we have independence. We verify independence. This definition, through some rearrangement here, and we're going to rearrange this, sort of extrapolate it a little bit further to get Bayes, we can verify dependence or independence of probabilities that we're looking at, right? If you're given the probability of various events, you can verify their dependence or independence from each other through this method of thought. So if you want to qualify that something is independent, this is one of the ways that you can do that, right? The intersection of those two things, the probability of the intersection of those two things is going to be the same thing as the probability of A multiplied by the probability of B. And if you want to think about that in terms of two coin flips, which are independent events, this should work, right? This should still work. So let's continue this thought process. Well, let's do a breakout first and see how this goes. All right, so here's Komogorov's definition above. That should be helpful. And I'll just read through this really fast. A survey of 400 vehicles was taken driving on an afternoon. The survey found that 175 of the vehicles were red, 120 of the vehicles were trucks, and 37 of the vehicles were red trucks. Given that a random truck is chosen, what is the probability that it is red? And given that a random red vehicle is chosen, what is the probability that it is a truck? So I'm going to set a timer. And I'll put 4 minutes on this. And yeah, try that out, and then we'll walk through it. Okay. So let me know if you want 2 more minutes on this, if you're still working on it. These kinds of problems are likely new to a lot of you, and they just take practice. So I'm happy to walk through it. Give me a thumbs up if you want 2 more minutes. Otherwise, I'll go ahead and work through it. Okay, I'm going to go ahead and work through it. Oh, cool. Okay. So I'm going to do this, pen and paper. To go through these kinds of problems, I think it's helpful, first write down what you know. We're talking about, given that a random truck is chosen, what is the probability that it is red? Given the random red vehicle is chosen, what is the probability that it is a truck? Well, let's write down what we know. We have the probability of a vehicle being red, right? Yep. So the probability of red is going to be 175 out of 400. And the probability of a vehicle being a truck, the probability of truck, is 120 out of 400. And the probability of red and truck, right? The intersection of red vehicles and truck vehicles. The probability of that is going to be 37 out of 400. So given that a random truck is chosen, what is the probability that it's red? Well, how do we ask that question? Well, we say the probability of red, like, given that a random truck is chosen. So that's the right part. That is the thing on which we're conditioning, is truck. Given this, what's the probability of that? Well, we can see that this is the intersection of this, 37 over 400. And that is over, what is the universe we're considering, right? We're considering the universe of trucks, which is 120 out of 400. And if I throw that into a calculator, which I'll go ahead and do, this is going to be 37 divided by 400, and that'll be divided by 120 divided by 400. And it looks like that is 0.308. So 0.3083. So that's one of the questions we're trying to answer. The other is that given that a random red vehicle is chosen, right? So that's the thing upon which we're conditioning. Given that, what is the probability that it's a truck? So this is truck. Probability of truck given red, and this is very similar. It's still 37 out of 400 over, but this time we're considering the universe of red vehicles, which is this 175 over 400. And so obviously we're going to get a different answer here, but notice that our numerator stayed the same. And I'm just going to reuse this. What was that? That was 175. And I'll just rewrite that part. And it looks like that is a probability of 0.2114. Okay, so hopefully that makes sense. This kind of question is fairly easy to answer in the event that you have some, certain information. If you have all the information at hand, these are fairly simple problems, right? If we know the probability of red, then we can answer this question very easily. If we know the probability of truck, well, we can answer this question really easily. And of course, if we know the probability of the intersection of red with truck, then we can answer both of these. And so this is kind of nice. It's given us all the information we need for this problem. The thing is, we're not always going to have all the information, and that's going to make answering some questions a little bit trickier. And I'm going to illustrate this through a disjoint space. And so here's our space S, and within S, we've got A. Okay, so all of that is A. And let's say that we have three regions in S as well. Okay, we've got B1 here, B2 here, and B3 here. So if we don't know the probability of A, if we don't know the how to describe the quote-unquote area of A, but we have other information, we can construct A by parts. We can assemble A through various intersections. So for example, the first intersection we might think about is, let's say, this one. What is the area of this? How could we describe the area of that part of A? We could describe it in relation to B2. That's one way that we could do that. Oh, we could think about it as we could potentially think about it as B2 minus A. But let's think about it as the intersection, simply the intersection of B2 with A. So that's one thing we can do. We can do that. We can do that. We can look at another chunk of this, and we can say, well, this is just the intersection of B3 and A. And we can look at this part as simply the intersection of B1 with A. And then we can compose A. We can actually just compose A from this, right? We can say that, well, just move this over really quick. Ooh. My sort of clip program has gotten buggy with the latest update to the Mac OS. I'm not a fan of Big Sur. I'm just going to say it. But yeah, really only for that reason, because it messed up my little clip program. So we can compose A, right? We can compose A as being the intersection of B1 with A, unioned with the intersection of B2 with A, unioned with the intersection of B3 with A. And this idea becomes more powerful, right? This all seems very abstract right now. It's like, okay, well, we don't even have numbers that we're working with. We'll get some numbers soon, and we'll see how this plays out. So remember when we rearranged Komogorov's law of total probability? Well, let's kind of do that again. So this was probability of A given B is the intersection of A with B. Wow. Let me just back that up. A with B over the probability of B. And we multiplied both sides by the probability of B, right? And what we see here is that the probability of A given B, the probability of A intersect B is equal to the probability of A given B multiplied by the probability of B. And from that, we can rewrite this whole thing in a really kind of convenient way. And I'll just demonstrate that really quick. So the probability, this first one, this area B1 intersect A, we can rewrite that, right? We can say that this is actually the probability of A given B1 multiplied by the probability of B1. Okay? So this comes from that, through that rearrangement of Komogorov's definition. And then union, we can think about this as addition, actually. And we can just add to this next part, which is the probability of A given B2 multiplied by the probability of B2, right? So that gets us that. And then we'll add to that, I'll just move it down here. This is the probability of A given B3 multiplied by the probability of B3. And thus we can compose the probability of A. So this kind of gets us from that kind of set theory approach back into the realm of probability through Komogorov's definition. So this is incredibly convenient. And let's look at this through an example. So here, let me grab this example. In probability, I think I've said this before, we're always talking about marbles and, different colored balls, numbered balls, like all kinds of, stuff that, of course, we're using every day in our real life, but we're not actually. But they help us to think about these problems, right? So we have two bags of marbles. Bag 1 has 75 red and 25 blue. So we've got this bag 1, right? And I'll just call this B1. And then we've got B2, which has 45 red and 37 blue. And we've got, in this first one, we've got 75 red. In the second one, we've got 45 red. And in the first one, we've got 25 blue. And in bag 2, we've got 37 blue. So what is the total probability that a red marble will be chosen if a bag is chosen at random with equal probability, right? And then a marble from that bag is chosen at random. So, what do we know? And, well, maybe let's start with what are we asking? We're asking the total probability that a red marble will be chosen. What is the probability of red? This is our question, right? Well, let's write down what we know. We know the probability of bag 1, and we know that that is equal to the probability of bag 2. And both of those are 0.5, according to the way that the problem has been written. We know we're thinking about the probability of a red marble, right? So let's write down what we know in relation to red. We know the probability of red given bag 1, which is going to be what? It's going to be 75 out of 100. It's going to be 0.75. We also know the probability of red given bag 2, which is going to be 45 out of 82. And that looks like, 0.549, let's say. So 0.549. And suddenly, we have all the information we need to start answering this question. What is the probability of red? Well, the probability of red is going to be the probability of red given ball 1 multiplied by the probability of ball 1. Okay? So this is going to be the probability of red given ball 1 multiplied by the probability of ball 1. Then we add to this the probability of red given bowl 2 multiplied by the probability of bowl 2. And thus, if we do that, we compose our sort of universe of red. And even though we're not told explicitly what the probability of red is in this problem, we can figure out what it is. And so red given bowl 1 is 0.75. So this is 0.75 times 0.5 plus 0.549 times 0.5. And if I just plug that in here, that was 0.75 times 0.5 plus 0.549 times 0.5. It looks like the probability of red is 0.6495. So we can construct this. We can figure that out, and it's not so bad, right? That's not so hard to figure out. So something that I might point out here is that in this case we have equal probabilities for bowl 1 and bowl 2, and we would get a very similar result, a very similar probability result, if we just add up 75 plus 45 and divide by 800 plus 74 plus, let me restate that. We could, if we add up the total marbles, which is 100 plus 145 plus 37, which I should just be able to do that in my head, but 182, great, okay. We could just divide 120 by 182, and why wouldn't we just do that? So this is a slightly different number. This is a slightly different number than what we're seeing here. We're seeing this 0.6495, but it's not so different. And this probability here is actually fairly reasonable, given that the probabilities of bowl 1 and bowl 2 are equal. But if we change the probability of bowl 1 to 0.2 or 0.7 or something else, and thus change the probability of the other bowl, then that is going to change this entire calculation, and our probability of red is going to shift, and that's important. And we can think about this pretty reasonably. If it's more likely, right? If we increase the probability of choosing bowl 1, then the probability of choosing red is going to increase, right? We can sort of think about that intuitively because of the ratio of red to blue in bowl 1. And so even if you're presented with some problem like this that looks like, oh, well, there's equal probability on this first choice, well, that's fine. I can just take our subset, our subset A, which is the sum of all the red marbles, and divide by the total number of marbles, and that should get me the right answer. Depends, right? It depends. It can get you the right answer. In this question, it gets you a nearly correct answer because the probability of bowl 1 and probability of bowl 2 are the same. But you change those probabilities, those initial probabilities, it very, very much changes how we need to calculate the total probability of red. So let's take 5 minutes and yeah, when we get back, we'll talk Bayes' theorem. So I'll see y'all back here in 5. All right, so let's pick up from here. What we've just described is, we can call this the law of total probability, right? So, again, what the law of total probability allows us to do is construct the probability of the universe that we're dividing by, what I'm going to refer to as the marginal likelihood. Possibly. More likely, I'm going to call this a normalizing constant. And the way that I'm going to think about this is we have some measurement of probability that is out of scale, right? Where this is 0 to 1, which is where our kind of standard, that's our standard probability. We want to pull this measurement of probability into the range 0 and 1. Generally, it's going to be smaller. It's going to be too small, right? Because, if you think about it, well, any probability that we deal with is going to be between 0 and 1. And if we're dividing by something that is less than 1, then it means that the numerator in our calculation is too small and we need to expand it. So this is in Bayesian thought, this is called the marginal likelihood. That is what we're constructing with the law of total probability. Okay, so let me just state this idea one more time. If we have B1 and B2 and B3, then the and we have A in relation to those disjoint areas, right? We have the probability of A is going to be the probability of A given B1 multiplied by the probability of B1 plus the probability of A given B2 multiplied by the probability of B2 plus the probability of A given B3 multiplied by the probability of B3. Turns out this is the crux of most Bayes theory problems. In that problem we just answered, we were just trying to find the probability of a red marble. And that's something that we could do. That's sort of a pure law of total probability problem. More often what we're talking about now is thinking of how to solve a different kind of problem when we don't know, for example, the probability of a red marble. So Bayes' theorem we can just write this down and set it aside, and we'll continue to sort of come back to this. So the probability of A given B, again, borrowing from Komogorov, that reworking of Komogorov's definition. Well, this is the probability of, we were saying A intersect B, but remember we can rewrite this as the probability of B given A multiplied by the probability of A over the probability of B. So this, I think throughout our materials we say, hey, don't worry about memorizing anything, blah, blah, blah. I'm actually, maybe I said this before, I'm actually a pretty big fan of memorizing formulas because you see them in other places. And I think Bayes is a great example of that. Anytime you see a Bayesian algorithm, you're going to see Bayes inside of it. And it's good to be able to recognize that. I think being able to think about what this probability of B means, we are constraining the universe for the operation that's sitting in the numerator. I think that is that's a good thing to know. There are some other names of things in here. Remember, I called the probability to be the marginal likelihood. We actually can also call that the prior or a priori value. The probability of A given B, we often will call that the posterior or a posteriori value. And we can think about that as like, well, this is a thing that this is a belief we might update as we continue through the process of observation. So let's think about this through an example again, and then we'll start just doing Bayes problems. So another thing we talk about kind of a lot, maybe too much, is cookies. There are two bowls filled with cookies. And we've got bowl 1 and bowl 2, right? So we've got bowl 1, bowl 2. Bowl 1 has 20 vanilla, and I'm just going to do this, 20 vanilla and 20 chocolate. Bowl 2 has 30 vanilla and 10 chocolate. And we're asking the question, given that a random cookie is taken from a random bowl, and each bowl has the same probability of being chosen, what is the probability that the cookie comes from bowl number 2, given that it is vanilla? So first thing, as always, write down what you know. Well, you know what I like doing with these first a lot of the time? I like writing down what we're asking. So if we look at this question, what is the probability that the cookie comes from bowl 2 given that it is vanilla? Well, I think that's I think we can just write that down, right? So what is the probability of bowl 2 given vanilla? And if we frame this through Bayes' theorem, and maybe I'll just snag the formula and put it up here, we can actually write this whole thing out right now and see what this looks like. So the probability of bowl 2 given vanilla is equal to the probability of vanilla given bowl 2 multiplied by the probability of bowl 2, and that's all over the probability of vanilla. Okay, so we've got that. Let's start writing down information. We've got it. So what is the probability of vanilla given bowl 2? First off, the probability of vanilla given bowl 2. Well, we've got, let's look at bowl 2. That's 30 vanilla out of 40 cookies, right? So that is 3/4. And we also need, we need some other information. We need the probability of bowl 2. Well, we know that the probability of bowl 1 is equal to the probability of bowl 2, both of which are 0.5. And even though it's not specifically expressed in this equation, we're going to need to know the probability of vanilla in bowl 1 as well. And the reason for that is, where does it tell us the probability of vanilla? It doesn't at any point tell us that. So we actually need to construct that with the law of total probability. And so to do that, we're going to need to know the probability of vanilla given bowl 1, which is just, it's just 0.5, right? So just say this is 0.75, and this is 0.5. So now the main question we have to answer is, what is the probability of vanilla? All right, well, if we're thinking about this in terms of that law of total probability, this is going to be the probability of vanilla in bowl 1, right? So the probability of vanilla in given bowl 1 multiplied by the probability of bowl 1 plus the probability of vanilla in bowl 2 multiplied by the probability of bowl 2. And that's how we can compose the probability of vanilla. So if we just fill this in, this is 0.5 times 0.5 plus 0.75 times 0.5. So that's 0.25 plus, what is that, 37.5? Well, I'll just put it in here anyway, just to add it up really quick. 0.5, 0.5, 0.75, 0.5. Okay. Except I need to do that in IPython. Okay, so it looks like that is 0.625. So, okay. So this all equal, the probability of vanilla just equals 0.625. Now we have all the information we need to answer this question. The vanilla given bowl 2 is 0.75. The probability of bowl 2 is 0.5. Probability of vanilla is 0.625. And we can answer that, the probability of bowl 2 given vanilla. So that's just 0.75 times 0.5, and that is divided by 0.625, which is 0.6. Okay, so I think at this stage, we want to think a little bit harder about what this problem means. What is this asking? And, if we think about this in terms of time, because I just want to frame this in terms of time, I think it's helpful. So at some point over here, you close your eyes, you reach out, and you pick a cookie, right? And then you open your eyes, and you look at that cookie. Somewhere in here, you chose a bowl, and this information is hidden, right? So, given which cookie you looked at, what is the probability it came from a specific bowl? That's an inverted way of thinking. It's a little bit weird. But, the more you do these, the easier that starts seeming. And I think with this problem, we noticed that it was more likely that we chose from bowl 2 than bowl 1, right? It was, a 0.6 probability that we chose from bowl 2, given that we had a vanilla cookie. And it makes sense because there's more vanilla cookies in bowl 2. The weight of vanilla cookies is greater in that bowl. Okay, so let's do a breakout. And this is the first Bayes breakout, and we're going to just do Bayes problems for the rest of class. I'll read through this, and I might hint at a couple little things. And we have Bayes' theorem right here. Okay. So given that a rare disease affects 1 out of 1,000 people in a given population, that's not actually a sentence, but that's okay. There's a diagnostic which has been developed. Semicolon. The diagnostic result is positive 99% of the time when it is given to someone with the disease. The diagnostic result is positive 2% of the time when it is given to someone without the disease. Given that someone has tested positive on the diagnostic, what is the probability that they actually have the disease? It's a very important kind of question, right? If you test positive for a specific disease, what's the probability you actually have it? Because it's not the probability you think it is, right? The diagnostic result is positive 99% of the time when it is given to someone with the disease, that doesn't mean that there's a 0.99 probability that you have the disease if you test positive. That's not what that means. And it's an important thing to consider for any kind of diagnostic. Okay, so go ahead and solve this. I'm going to put 6 minutes on the clock. So I assume a couple of you are still working on this, trying to figure it out. I think it's helpful if, especially this one, I'm going to go ahead and start walking through it, and continue to work on it if you feel like you're almost there. I think part of these problems, these sort of textbook-based problems, a big part of it is figuring out the workflow to solve it, and so I'll go through that workflow. So the first thing is let's think about the question that's being asked, right? Given that someone has tested positive on the diagnostic, what is the probability that they actually have the disease? Well, I'm going to call that the probability of the disease, having the disease, given having tested positive. The first thing I'll usually do is I will write this out in the Bayes construct. So this is just the probability of testing positive given having the disease multiplied by the probability of having the disease over the probability of testing positive. Okay, so now I'm going to write down what we know. And, what this tells us, the probability of having the disease, right? The probability of having the disease is 1 in 1,000. The probability of testing positive given having the disease, we know that's stated explicitly. It's positive 99% of the time when it's given to someone with the disease. So the probability of testing positive given having the disease is 0.99. And the probability of, well, is that all it gives us? Oh, the diagnostic result is positive 2% of the time when it's given to someone without the disease, okay? So that's going to be the probability of being positive given not disease, and that's 0.02. Okay, so this is what we're given. There is a piece of information that's hidden in there, implicitly in there, and there's some stuff that we need to extrapolate. So what can we fill in first? Probability of testing positive given having the disease is 0.99, and the probability of having the disease is 1 in 1,000. Now, we don't know the probability of testing positive, and that's kind of the crux of the problem. So the probability of testing positive is going to be all instances where it's possible to test positive. So, so how do we think about this? This is going to be the probability of testing positive given having the disease multiplied by the probability of having the disease. And we're going to add to this the probability of testing positive given not having the disease multiplied by, well, we don't have this other value explicitly, but we do have it implicitly, the probability of not having the disease. So we can fill this in. This is going to be 0.99 multiplied by 1 in 1,000 plus 0.02 multiplied by 999 out of 1,000. Okay. So let's figure that out. Or let's plug that in and see what that is. So that's 0.99 multiplied by 1 out of 1,000 plus 0.02 multiplied by 999 out of 1,000. And it looks like that is 0.02 let's say, let's use all of those, 0.02097. So that's the probability of testing positive. And now we have all the information we need to solve this. So this is 0.02097. If somebody got a different probability of testing positive, just let me know. I may have made a typo somewhere. So barring that, let's just plug these in and see what we get. So this is 0.99 times 1 out of 1,000. And we are dividing that by 0.02097. So it looks like, and this may be surprising, it looks like the probability of having the disease given having tested positive is 0.0472, let's say. That's a 4.72% chance. That might be surprising, right? Like this gives you a sense of what diagnostic tests mean. And so, like, let's say you go in for a screening for a particular illness. That initial screening is often meant to catch a lot and sometimes be wrong. And let's say it's 99%, when somebody has the disease, it discovers that 99.9% of the time. But let's say that disease is super rare in the population. Well, you need to ask the question, what is the probability of having the disease having tested positive? Because that number is often much, much lower than you think it would be. And in a lot of testing scenarios, they'll test you, and then they will follow up with another test. And you would see in a follow-up test that this would suddenly increase the probability of having the disease quite a bit if you tested if you tested positive again on perhaps another diagnostic. So that is a Bayesian approach, and it's very common in diagnostics. So let's do another one. This is going to seem sort of like a brain teaser, and I really like these kinds of problems because they're kind of imaginary and weird. So Freddie remembers to take his umbrella with him 80% of the days. It rains on 30% of the days when he remembers to take his umbrella, and it rains on 60% of the days when he forgets to take his umbrella. What is the probability that he remembers his umbrella when it rains? So I'm gonna put 4 minutes for this one, and do your best on it. Okay, so I'll start walking through this. And, don't be discouraged if these aren't coming naturally. They're not particularly easy, unless you've done them a lot. So, practice them, find more of them. We're likely not going to get through all the problems. We're probably going to do one more in this set, and I think there's a couple more in the slides. So let's just walk through this. So Freddie remembers to take his umbrella with him 80% of the days. I'm going to just immediately write that down. I'm going to call that the probability of umbrella, and I'm going to set that at 0.8. It rains on 30% of the days when he remembers to take his umbrella. So this is implying some sort of causal relationship that we'll just accept tacitly. But this is the probability of rain given umbrella, and that is 0.3. And then it rains on 60% of the days when he forgets to take his umbrella. So I'm going to call that the probability of rain given not umbrella. And that is 0.6. What is the probability that he remembers his umbrella when it rains? So the question we're asking is the probability of umbrella given that it rains. And we can immediately, convert this into the Bayes form. So probability of rain given umbrella, we know that, multiplied by the probability of umbrella, we know that, divided by the probability of rain, which we don't know. And this brings us back to the law of total probability, which is, like I said, generally the crux of these problems. So the way that we can think about the probability of rain, well, we can have rain given umbrella and rain given not umbrella, right? So this is just going to look like the probability of rain given umbrella multiplied by the probability of umbrella. And then we add to that the probability of rain given not umbrella multiplied by the probability of not umbrella. We can fill these in. Rain given umbrella is 0.3 times umbrella is 0.8. We add to that rain given not umbrella, which we know as 0.6. And then the probability of not umbrella, well, we don't know that explicitly, but we do know it implicitly. It's just the complement of the probability of umbrella, so it's 0.2. And we can plug that in to a calculator or the next best thing, which is this. So that's 0.3 times 0.8 plus 0.6 times 0.2. And that's 0.36. Probability of rain given umbrella, again, is 0.3. And then probability of umbrella is 0.8. So let's look at what that is. That's 0.3 times 0.8 divided by 0.36. And it looks like the probability of rain, the probability of him taking his umbrella given that it's going to rain is, we can just say 0.667. Right? 2/3 probability. Okay, so let's look at another one. And this one has a little bit more complexity to it, but ultimately it's reasonably as simple. We just have more items, you could say, that we're considering. So I'll go ahead and read through this. A glazier buys his glass from 4 different manufacturers: Super Clear, See-Through, Bird Trap, and We Sell Glass. And we have the rates at which he buys that glass. In the past, the glazier has found that 1% of superclear products is cracked, 1.5% of see-through product is cracked, and 2% of bird traps and we sell glasses products are cracked. That would be 2% for bird trap, 2% for we sell glass. The glazier removes the protective covering from a sheet of glass without looking at the manufacturer's name, right? It's a random choice. Finds the glass is cracked. What is the probability it was made by bird trap? Okay, so let's do 5 minutes on this one. I think it's reasonably more complex. So let's do 5 minutes, and then we'll have enough time to solve it. Okay. Okay, I'm going to start walking through this. It's going to be a little hard to read that, but I think it'll be fine. Okay, so a glazier buys glass from 4 different manufacturers: super clear, see-through, bird trap, and we sell glass. And I think the first thing about most of these is like, well, how do I organize this? I'm just going to say see-through, super clear is S, okay? And that is 0.1, right, 10%. And then I'm going to call see-through ST, just to have these be easy. So that's 0.25. And then bird trap, I'm just going to do B. Probability of bird trap is 0.3. And then the probability of we sell glass is 0.35. The glazier found that 1% of super clear product is cracked. So we've got these other probabilities. Cracked given super clear is 0.01. Cracked given see-through is 0.015. Cracked given bird trap is, what is that? Is 0.02. And cracked given whatever's left, what is that? We sell glass is 0.02. And then the question that we're trying to answer is, what is the probability that it's bird trap given that it's cracked, right? So you look at it, it's cracked. What's the probability it came from bird trap? So we can write this out. Bird trap given cracked is the probability of cracked given bird trap multiplied by the probability of bird trap over the probability of cracked. And notice we don't know what that probability is. We're going to have to compose it. So probability of cracked is going to be, well, it's kind of nice. We've got all this kind of lined up, right? And we can see this as the probability of cracked given, what is that? Super clear, multiplied by the probability of super clear. And we can add to that the probability of cracked given see-through, multiplied by the probability of see-through. Add to that the probability of cracked given bird trap, multiplied by the probability of bird trap, and then the probability of cracked given we sell glass, multiplied by the probability of we sell glass. And we can just fill these in, right? So that's 0.01 times 0.1 plus 0.015 times 0.25 plus cracked given bird trap, which is 0.02 by 0.3, and then cracked given we sell glass, 0.02 by 0.35. And just add, we can just figure this out. 0.01 times 0.1 plus 0.015 times 0.25 plus 0.02 times 0.3 plus 0.02 times 0.35. So let me just scan back over those. Those all look correct, I think. And it looks like that is 0.01775 for the probability of the any glass being cracked, right? So that's 0.01775. Okay, so cracked given bird trap is 0.02. Probability of bird trap is 0.3. So we can calculate that a little bit further. And 0.02 times 0.3 divided by 0.01775. So it looks like that is roughly 33.8%. And if you want to reason these out, and I think it's a good idea to reason these out, look at the probability of bird trap in the first place. Now, I would venture to say that it's going to be more likely that the glass came from we cell glass than bird trap, right? Because notice the weight of we cell glass is 0.35, and the probability of being cracked is the same, right? So you can do some reasoning here, not just blindly plugging into a formula and figuring these out, but it's always a good idea to try to explain this to yourself later. And it kind of makes sense when we look at these values, right? That we have something that works out to 1.7% probability that the glass will be cracked in general. I think there's a lot that we could deconstruct there. So that's class for today. These aren't easy. You have to practice them, and I definitely recommend going back over these worked problems and at least once and kind of figuring them out again. The other thing I want to mention is that we're heading into interviewing quite a bit for the May 17th cohort. If you're trying to get into the May 17th cohort and you're not sure of your strategy, how you're going to get into that class, reach out to me, I'll connect you to probably Lance or Devin, at least for this week, or Clark, and figure out your timeline, right? We're getting to a sort of crunch time. You don't want to wait to the last minute to interview if you can. Try not to do that. And, get in touch with us, work with us. We'll help you figure out what your timeline actually looks like. So you can message me, message Clark. I would start with us. And then we'll probably connect you. Or if Clark has bandwidth, he'll connect with you. I won't have bandwidth until after next weekend, as it turns out. But yeah, definitely reach out on Slack, and I'll get back to you and connect you to someone on our team. And they'll help you get a sense of where you are in relation to passing the interview. But yeah, stay on if you have any questions. I'm going to stop recording.